idea behind this piece is to capture the ever-changing atmosphere in the atrium of the CSIS building. From the crowds that congregate after lectures to the post 5 p.m. stillness. IR sensors are used to capture foot traffic in the atrium, and this information is used to control a system of solenoids to strike tone bars taken from a glockenspiel. Every hour, a composition will be played that reflects the last 3 hours of activity. Busier periods are represented by the tempo and intensity of the piece increasing, and similarly, quieter periods are represented with a calmer output. The composition, we drew a lot of inspiration from various minimalist composers such as Steve Reich and Terry Riley. Riley's piece in C was of particular interest when designing the rule system that is used to translate activity into sound. In C consists of 53 short predetermined musical phrases or rules. These rules were designed so that they be played in any order for any length of time and yet still result in a piece that is both rhythmically and melodically interesting. We wanted to create a system similarly where any combination of predetermined musical phrases would result in a coherent piece of music. We also aim to incorporate elements from the music of Steve Reich. One of the solenoids provides a steady rhythm that remains solid for the entirety of each composition, and the other solenoids then phase in and out with this steady pulse at various tempos depending on the activity that is being represented, and this phasing is an element that is seen a lot in Steve Reich's music.
It fell to the data analysis team to decide the parameters of data collection in terms of time frames, as well as the temporal transformation by which these time frames would be compressed into musical output. It was already decided that slave output would be standardized into discrete 5-second units of music. It was necessary to consider the expected aesthetic outcome resulting from the different possible ways of sampling and representing the data. The following factors were considered: the size of the data collection sampling window, or frame as it's known, the frequency of performances, the variation in the output from one performance to the next, and the length of the performance or composition. The following parameters were adopted. 7 minutes of real-time data collection would constitute a frame. This offered a sufficient sample size without homogenizing the input data. 9 frames would constitute an act. 3 acts would provide the full data set for generating a composition. Each of the 27 frames comprising the composition would be translated, as it were, to a single rule, resulting in a composition consisting of a linear sequence of 27 rules. It was also deemed appropriate to schedule a performance every 9 frames. This means that the data collection window is out of phase with the teaching schedule and its associated regular rhythms of building activity, thus ensuring greater variation between compositions. By virtue of the ratio between the data collection time span and the time between performances, 3:1, the 3-part or 3-act compositional structure emerges. Inevitably, only 1/3 of the material in every performance is novel. With every successive performance, the oldest act is dropped from the beginning and the novel act is appended to the end. The mapping of sensor data to rule output is straightforward. The masternode Arduino registers any trip of the IR sensor and increments a simple integer count associated with the current frame of time. Counting is continuous and is virtually uninterrupted during playback. A new count is started with every new frame. When the time comes to play the composition, these count values must be translated into rule numbers. The rules were already arranged on an intensity scale from 0 to 49. Count values are mapped to the intensity values in direct linear proportionality, with busier periods or frames resulting in more intense output. Each count value is compared to a reference maximum count value, equivalent to Rule 49 in terms of output, in order to determine its relative position on the scale. It is impossible to estimate a value for the reference maximum count value that will guarantee that the full dynamic range of the rule set is utilized effectively over time. So rather than fixing the reference value, the approach taken was to adopt the last highest sample observed as the new reference maximum value. The master node is multifunctional. Essentially, it needs to gather data via the connected IR sensor and then generate and output a composition based on that data. Playing the composition means issuing a series of specifically timed rule numbers via the built-in UART TTL serial interface. The requirement of multifunctionality engendered certain program design challenges. On the one hand, the Arduino must be responsive to changes in the IR sensor signal at all times so that it does not miss any trips of the beam. On the other, it must process and send composition data to the slave nodes at precise times. This potential scheduling conflict was resolved with the decision to prioritize composition playback to the exclusion of all other processes when a buffer window or lead time immediately prior to any note being played is entered. During this buffer, the Arduino stalls using the delay function until it is time to send the note via the serial port. The length of the buffer was optimized to minimize blocking time and reduce the likelihood of missing a change in the IR sensor signal.
Hi, my name is Kyle. I'm going to talk to you about the slave code for installation B. So the first thing in our code is the global variables, which we use repeatedly throughout the code. The first one is a constant int called myId that signifies which group slave the code is. Then we have int data received, which is the variable we'll use to store the incoming serial data from the master Arduino. The variables here, int, off, s, m, and h, are what we use for the hardness of the strike of the solenoid. I'll discuss more about them later. We have int a and b, which signifies what pins we're going to use for our solenoids. Long time is the variable that refers to the total length of each musical phrase. We use this variable for calculating various delays in our code. Then in our setup we have pin mode, which sets pins A and B to output. Then we have serial.begin, and we set our baud rate to be 9600. Then in our loop we have an if statement, if serial.available. And this is constantly checking for incoming data from the master Arduino. Then below that we have a serial.read. And if the data is available, it gets stuffed into a variable called data received, which we initialized earlier. After this we have a switch statement which checks our data received variable. Obviously the numbers coming in from the master should be from 0 to 49 as we created 50 rules. So essentially if we receive a 0, the function rule 0 is run. If we receive a 1, rule 1 is run, and so on, all the way up to rule 49. We created each rule separately so we could call each one individually. Each rule consists of a serial.write, which sends the corresponding rule number to the next Arduino. Then below that is another function call which calls to the function that controls the solenoids. We simply pass down arguments to the function with each rule as to avoid hardcoding each one, which would just take ages. As you can see, the arguments in rule 0 are a, s, time divided by 2, and 2. The a refers to what solenoid to use, so it can ever only be either a or b. The s refers to the power at which the solenoid strikes the glockenspiel note. The s means soft. The other arguments that can be there are m for medium and h for hard. So the value here is an analog value, or a PWM wave, which gets written out the analog pin. It can be used to light an LED at varying brightness or drive a motor at various speeds. We were hoping to use these PWM values to strike the glockenspiel at different strengths, so basically have softer and louder notes, but the difference was way too subtle, so we just set all of them to be the same value, and that value was 250 in the end. Time divided by 2 is our total time divided by 2. We use this as a delay between the hits of the solenoid. Then the final 2 refers to how many times the solenoid must strike the glockenspiel note. Then as you can see, we repeat the passing down of arguments for each rule throughout, for the entire 50 rules. And then in our function we have it set up to receive arguments, as I just mentioned. So what solenoid to use gets passed into int x. Then the power of the solenoid strike gets passed into hardness. Then we use these values, as you can see, in our analog write function. The delay of 10 milliseconds is the speed of the solenoid strike. We experimented and it turned out that 10 milliseconds was the ideal speed for a good clear ring of the glockenspiel note. The long rate argument is the delay we use for the solenoid to be idle between hits of the note. The value it's equal to is the total time of 5 seconds divided by the number of solenoid hits. So if we want to hit the solenoid twice in 5,000 milliseconds, that would mean the 5,000 milliseconds is divided by 2, and thus the long rate argument would be equal to 2,500 milliseconds. We then do an extra simple calculation to this. We take 10 milliseconds off, as that's the time it'll take for the solenoid to strike. So now the new value is equal to 2,490 milliseconds. We then pass down that new value as the time for the solenoid to remain off. The int times refers to the number of times the for loop is iterated in our rules. It can range anywhere from between 1 to 50. Then we have this extra function is essentially the same as the first function, except it controls both solenoids at the same time, as opposed to the first one, which only controls one at a time. The reason for this is some of the rules the master sends requires the 2 solenoids on each slave to play at the same time. And that's essentially our slave code. All the slave group codes are very similar. There are 5 different sets of slave code, however, and they all just have slight variations in structure and names of functions and variables and so on, but they're all working off very similar principles. There are a few tiny debugging things that I didn't mention. They're not important in the overall functionality of the slaves. They're only little small debugging things in our code to help us figure out problems in the development stage. So that's all from me. Thank you.
Hi, I'm CJ Hartigan, and I was part of the wiring and soldering team for this installation. The circuit design for the project was a very important aspect to get right, as the work from the coding teams needed hardware which was capable of producing a consistent and reliable output every time. The original design drawn up was basic, incorporating 2 solenoids per circuit and an LED which would flash in accordance with the solenoids firing. Their purpose was to aid debugging. We needed 6 circuit boards, 1 for each group, with the master sporting just 1 firing solenoid and every other board holding 2. 2 output wires allow the Arduino to control each solenoid through the Arduino's pins. The board is grounded from the power supply and shares a common ground with the Arduino. We used 2 10K, 1 47K, 1 150 ohm and 1 220 ohm resistor per circuit, later on implementing the use of diodes to aid the flashing of the LEDs. The finished circuit will be powered by 24 volts from the wire strands, which contain 24 volt power source for the solenoids, 5 or 6 volt power supply for the Arduinos, and a grounding wire.
Hi, my name is Conor Linehan, and I've been selected to speak as part of the design team for our installation. So as part of the design team, one of our main goals was to come up with a diagram for a design that we felt was aesthetically pleasing and straightforward. After making up several mock diagrams, we decided that an N shape as such would be the easiest, with a no block hanging on either side and a solid piece of material to give us enough space to mount our Arduino, our circuit board, and our solenoids and our note blocks. So after drawing the diagrams and coming up with the best solution, we felt that the next step then was to gather materials which we felt would be easy to use, lightweight and portable, as well as cost effective. So we decided on corrugated plastic, as was plentiful supply. After this, we met up with our soldering team to remind them just how our design was going to look, give themselves enough wire and enough length in case they needed a bit of extra or a bit less. So after this, we got the corrugated plastic and molded it on with hot glue. So what we did was we used 1 piece on top and 1 piece underneath it, so that we give ourselves a bit more strength and a bit more space to work with when it comes to bolting down solenoids. Our next step after this was cut up the glockenspiel wheel into several pieces, so each group got 2 except for the master group, which got 1 glockenspiel wheel, and we decided to call them no blocks just for future reference. After this was all done, and after the circuits ready from the soldering team, what we decided to do was measure out our solenoids as the length of the throw from the solenoid had to be perfect distance away from the note block. Once this was all measured up, we secured the solenoid to the board using bolts and nuts, and then after this we secured the hanging of the piece, as we decided that a simple strip of wire would be the easiest and most effective way of doing this, as it was easy to use and readily available. So once we had the holes drilled in the piece for the wire and we tested its tensile strength, we were happy enough that it would be able to hang from a distance without too much trouble. So once we had our holes drilled for our solenoids and everything in place, all we had left to do was mount our Arduino and mount our circuit, which was done just using simple double-sided sticky tape.